Once we know the basic curve, and we saw this idea last year, then shifting it or transforming it into another curve can be possible, again, if we recognise it. So we know y equals function x is some basic curve. We can shift it somewhere on the number plane. I guess the first idea we saw was just shifting it up or down. So if we add a number to it, it will go up or down, however many we add. Another way of thinking about that is when it's grouped with the y value. See, I can move that a with the y. I can't move the a with the x value because the x is inside the function. So even though it's on the other side, I can think of it as grouped with the y. And the reason I think of it like that is it reminds me it's the y value that's going to be affected here. So it moves up or it moves down a units. Okay. Now, if you're ever unsure where it's shifted to, once you move it to the other side, just ask yourself, what would make this equal to 0? Solve that and then you know where it's being moved to. So here's a random curve, y equals function x. If I wanted to move it up a units, every y value gets moved up a units. There's my new curve, function x plus however I've moved it up, so plus a. Now, when I group it with the x, so now this time it's grouped with the x, it's inside the function, so I can't move it to the y because it's inside the function, so now it's horizontally it's going to be changed, or horizontally it's going to be shifted. And that'll be, again, be left or right, and if you're unsure which way it goes, again, ask yourself what would make this equal to 0. So if I was to move it to the left b units, so the whole curve would go across b units, I'd end up with the new curve. That would be function x plus b, because I've moved the origin over to negative b. I've moved a b to the left. Okay. What about stretching curves then? So that was shifting them. What about stretching them? If I have a constant times function x, now once again, this is grouped with the y, because the x is inside the function value. So the k could go with the y value. And we stretch it vertically by a factor of k. So theoretically, it's y divided by k. Now, if that constant is less than 1, I'll end up with a shallower curve. If it's greater than 1, I'll end up with a steeper curve. So that would be an example of k times function x. Every y value, if you like, has been multiplied by k, thus making it taller and steeper. That is k greater than 1. Shallower would be k less than 1. Okay? But notice things like this. The x-intercepts have not been affected. It's the y values that are being affected. So the y values, other than the x-intercepts, the y values have all been changed, multiplied by the value k. Okay? So the domain, although for our random one here it's all real x anyway, but the domain would remain the same. Okay? But it's those key values, the x value, the key values are the same, the x-intercepts are the same. So the stationary point is still at the same x value. It's the y value that's changed. So that's what I mean there by the x values of key points will stay the same. Whereas when it's grouped with the x, again we think of it as x divided by the k, same as the other one could be written as y divided by the k, it gets stretched. The interesting thing is it still is, if k is less than 1, it ends up getting steeper, and if k is greater than 1, it ends up getting shallower. There's a curve that got steeper. K is less than 1. You can think of it as pushing it in. And so it sort of gets all bunched up, thus getting a steeper curve. If you prefer to think of it as a constant times x, I'll call that capital K, then okay, but capital K in that case would be greater than 1, not less than 1. If k was greater than 1 with our x divided by k, then I'm pulling it out. And so that has an effect of making it shallower. But now have a look at the key points. It's the y values that have stayed the same. Okay? So have a look at, say, that maximum point over there on the left. The y value is still the same, it's the x values that have changed, because that constant is grouped with the x inside the function. So in this case, the range of the curve has stayed the same. The y values of the key points stay the same. The y-intercepts will stay the same. Next idea is reflecting curves by using negatives. So y equals negative function x, we reflect the curve in the x-axis. Basically, we're saying every y value, we're changing the sign. So it was positive 2, it's now negative 2, and so on. So there's our original curve. Once again, the x-intercepts will stay the same because negative 0 is 0. But that y-intercept, which is down there at negative something, will become positive something. Those stationary points, again, the negative becomes positive, the positive becomes negative, and it has the effect of reflecting in the x-axis. So there's y equals negative function x. Function negative x now reflects in the y-axis, because now we're substituting in the negative value. So instead of substituting in positive 2, we're substituting in negative 2. So the y value will stay the same. Sorry, the y-intercept will stay the same. But now those key points, look at those x-intercepts, I've reflected them in the y-axis. The stationary points, reflect them. And there we go, there's our curve reflected in the y-axis. So that's function negative x. Here's a special one. Function 2a minus x. So everywhere there's an x, we're replacing with 2a minus x. That reflects in the line x equals a. Okay. So it's a more generalised one of function negative x. Function negative x, I guess, was simply when a was equal to 0, and so you reflected it in the y-axis. But if you have something minus x, it's still a reflection, but the reflection has shifted, if you like. So there's function x. Let's say there's x equals a. So we're going to reflect in that green dotted line. Well, fortunately, my turning point there was on the line, so that will stay the same. But the y-intercept will reflect in the green line. The x-intercepts will reflect in the green line. And the other stationary point will reflect in the green line as well. And so we get a reflection, but this time it's not in the y-axis, it's in the line x equals a. So if you see 2a minus x. Similarly, you can reflect horizontally, but just not in the x-axis, if it's 2a minus function x. So it's a more generalised one. Okay. So that would reflect in y equals a. So let's put a horizontal green line there, and we're going to reflect the original curve. So anything that's on that green line will stay in the same spot. Let's get all the other key points. The x-intercepts, the y-intercept, turning points, and there we go. There's a reflection in the line y equals a. Some books you'll see it written as function a minus x, but then they say reflect in the line x equals a on 2. I just find it easy to think of it as 2a, and then I just got to divide it by 2 and I get where the reflection is. Yeah. See how we go.